when the points are equidistant, where you use Newton's interpolation formula. That is, you have the Newton forward and Newton backward is one we looked at. And I think I told you to go and look for the Stirling formula. Did I? So, and also we looked at now the interpolation in cases where the points are not equally spaced. You might go to the field and you collect data and your measurement points or the recording points are not equidistant from each other. So in that case, you need the case where you can deal with points which are not equidistant from each other. And that's where now the Lagrange came in. And now we get the Lagrange interpolating polynomial where it deals, so it's general. If the points are equidistant, you can still use the Lagrange, and Lagrange will be the same as the Newton formulas. But so Lagrange is general, that it can handle even the points which are not equidistant from each other. And to derive the Lagrange formula, we started by looking at the divided differences. And so basically the divided differences are the cases where you find the difference between the function and then you divide by the step size. That's the divided differences. So did you find time to go through the YouTube channel? I did not. Sasa tukiruka vitu zingine utajuaje kama tumeruka? But so yeah, it's just my recommendation that at least if you go there, you can get more information, you can read some of the things, and then you can also, I think the books I gave you also have interpretation, right? Also read the things I gave you, then you get different view. But even if you read and you get a different notation, you just understand things and put them in the notation or the form in which you understand better. And so before doing, let me just recall a few things we did. So we said that the divided differences so the divided difference between 2 points x0 and x1 is simply f of x0 minus f of x1 divided by x0 minus x1. You can start with the other way around. I think there is no problem provided you keep the same order. And so we said that if you have a linear approximation, then if you find the two divided differences must be the same, it's just like the linear equations. These things are equivalent to the gradient. And so if somebody notices that if I find the final difference of this is the same as so this is over h is the same as the divided difference between what the point x0 and x1, so they are equivalent. And then you can generalize that the kth order divided difference is just the finite difference over k factorial h raised to power k. You can prove this. So they're basically equivalent to what? To the Newton's formulas. And so this is the first order divided difference. The second order divided difference, meaning if you find the divided difference between 3 points and then x1 and x2. So this is simply the divided difference of the first divided difference. So this will be given by, that is x0, x1, and then minus, it's supposed to be, I think, x1, x2, and then divided by, that's x naught minus x2. So that gives you the second order divided differences. So you simply take the divided difference of the first order divided difference, and then you can see that this can be generalized. Even you can find the kth order. Notice that I'm starting with this, but you can start with even this part, as long as this will take care of the negative. So in general, the kth order divided difference, that means the divided difference of the k points 1 until xk is the same as what? It will be the divided difference of the divided difference of now the points. So that is x1 into xk minus the divided difference of x naught into xk less 1, and then divided by xk minus x naught. So just notice that in this part I've just reversed this order, but still it's still the same. And so to derive the Lagrange, or first I told you, I think there is something I wrote here when I derived the Lagrange formula, that the easiest way to write these divided differences is by writing them in which format? In this format. So it is f of xi over xi minus xj plus. So you can keep on summing these divided differences as you go along. So in this case, but otherwise, if you write even in the other format, it's still okay. So this other format just allows you to evaluate it in a much easier way. And so, for example, just to keep in the same notation, that this divided difference x naught, x1, x2 can be written as what? It is f of x naught divided by the x naught minus all the other ones, and then into x naught minus x2, and then plus f of x1 divided by x1 minus x naught, and then into x1 minus x2, and then plus f of x2 divided by x2 minus x naught, and then x2 minus x1. So these parts can be written in this way, and then you can express all the kth order differences as the sum of these fractions. So is there a question until that point? So I'm just revisiting this just by defining more the first order, the second order difference, the third order. But so from these differences, if you define the first order difference and you want a linear polynomial, it means now if you find the second order difference, it will be constant. So in the way we derive this by equating the 2 points here, you can just say that if you want a linear polynomial, then the second order difference should be a constant, and you give this point a general point x. So basically what we are saying is, if I put here x, this should be 0, and if you simplify, you will get the same Lagrange polynomial of the first order. And then if you want the second order polynomial, it means the third difference will be constant, equated to 0. Equal to, so not constant, is equal to 0, it vanishes. If you want a third degree Lagrange polynomial, then the fourth difference will be 0. That's how you can drive the Lagrange. But so we said in general, just the Lagrange polynomial, let me write it in compact form. Lagrange polynomial is given by what? Is given by f of x is the same as, can I write this way? I is equal to 0 up to n, then you have Li of x, then f of xi, where Li of x is the same as, is, when I write this, I mean the product k is equal to 0 up to n. K is not equal to I of x minus xk divided by xi minus xk. When I put it this way, is it okay? When I put it this way? And this is much easier for somebody who wants to program this. You just write, you're having all these products of x minus xk except the xi itself. So k cannot be equal to I. So this formula basically is similar to the format in which I wrote it. Yeah, it's the same thing I wrote here. It's just the same as in this. So if k, for example, is equal to 1, you can extract it. If k is equal to 2, you can extract it. Just internalize for 1 second and tell me, so that we can look at an example now. Any question? So if there's no question, let us do an example. So anybody wants to give us an example? Of the point of any application, you give us a point, and then we can use Lagrange to find this. Anybody with an example in mind? Hakuna? So I can just say maybe number 1, find f of maybe 2.5 given the following data set. And so we have here x and then f of x. So you have a function whose, so here this is -1, this is 7. You have 0, this is 10. You have 2, this is 22. And then you have this is 5, and this is 235. So when you get such a question, even if we don't tell you to use the Lagrange polynomial or the Lagrange interpolation, then you just look at this point. They are not equidistant, so you cannot use Newton's interpolating polynomial. And so we need here the Lagrange polynomial. Can somebody tell me, since we are getting, what is the order of the polynomial we can get from this by Lagrange? What will be the order of that polynomial? What is the order of that polynomial we can get from this? Mhm. Are you still there? Are people still in this meeting? The problem is that I don't know how to teach a class which is quiet.
I will try by saying order 3.
Order 3, why?
Yeah, I've looked at the formula and I'm seeing that the for the X, the data set, the formula, I'm seeing that if you have 4, you'll have an order of 3.
Yeah, okay. Yeah, that's true. So for the Lagrange, if you have n points, then you can get a polynomial of n minus 1. In fact, that even is also in the Newton's formula. The order is always 1 less than the data points. So that is true. So once you know that we need Lagrange, so we have x naught, x1, x2 until x3. And then we have the corresponding y's. So you can now write down the formula for the Lagrange. We know that now the polynomial, let me just write now here, p of x will be the same as L naught of x multiplied by f of x naught plus L1 of x multiplied by f of x1 plus L2 of x multiplied by f of x2 and then plus L3 of x multiplied by x3. And so what you need is just find all these Li's and then you evaluate them. And so can somebody tell me what will be the L naught of x? I want to see if you can now rewrite this formula in expanded form by picking out different values. So can somebody read to me the formula for L naught of x here?
X minus x1
X minus x1
into x minus x2
uh-huh,
divided by x naught minus x1
divided by x naught minus x1
into x naught minus x2.
minus x2. Uh-huh. Done or
Done.
done? Kuna mwenye ako na pingamizi?
Yes.
Yep.
X minus x3 on the numerator.
Yeah, in fact, I was starting to write it. And then here,
X naught minus x3.
x naught minus x3. So what she said was correct, but it was only for these points, right? So this point was being eliminated. So if you want to know the order, then if you expand this, you will have x multiplied by x multiplied by x, you will have x cubed. By the way, these Li of x are called the Lagrange operators. So these Li's, they are the Lagrange operators. And so each of this Li, in this case, will be a third degree polynomial. It's not a fraction because no, it's a fraction, but it's a polynomial. Why? Because these are constants. They are known values. You only have an unknown value here, which is x, which is only which makes this to be a polynomial, right? And then we are evaluating what? We want to evaluate f of 2.5. That means our x is 2.5. So can you evaluate L naught of x? So L naught of 2.5 will be 2.5 subtract. No, somebody can give us just these differences. We don't have to subtract here. It's just 2.5 minus x1 multiplied by 2.5 minus x2 multiplied by 2.5 minus x3. That one, that's what I need. The difference here, give me the differences.
Two point five.
Hmm?
2.5.
2.5 again. Or are you giving us the whole product, or you are?
Differences.
But what is? Oh, okay. Oh, yeah. Okay, I was subtracting the wrong one. So that is 2.5 multiplied by
Multiply by 0.5.
0.5.
0.5 multiplied by
Negative 2.5.
Negative 2.5.
2.5 divided by this one. You can even just give. I'm just doing this stepwise, but if once you know this, you can just plug in this one and then you give an answer here. So just doing this stepwise so that people can see what is happening. The differences here is, what are the differences here?
-1.
-1.
-2.
-2.
Wait.
Is x naught -1 minus -1? That's
It's
negative.
-1. It's -1.
That's -1 and then -3, right? And then
Yes.
negative and -6. And so you can get this. No, so I think people know what is happening, right? Because so I've seen that if we keep on, if we have to wait for you to do these computations, then we are just wasting time. Because you are, I think, some of you maybe, I don't know. So in the same way, can you tell us what is L1 of 2.5? Then you can just change values. In fact, once you know this general formula, Li, and then you put this I. And so if you want L naught of 2.5, you just keep this 2.5, and then you are changing only these other terms. So you can get all those values, and then you plug in into this. So the advantage of Lagrange, since it applies to any general interval, the step size, it can be used to compute the inverse of a function at a certain point. Basically, so you know what you are doing, like even for the values, is that we need x to compute f of x or y. But if you bring the Lagrange, then we can find the value of x at which y is given. For example, I can tell you, can you find x when, for example, y is maybe here, you can even say here maybe is 50. That means the reverse process. Because once you reverse the process, then you are not guaranteed of the equidistant. So in that case, you cannot even use the what? The Newton methods. So I can just pick this example. For example, you have these data points, and the data points are, why does it delay? So I have this is 20, and then 354, and then 25, 332. I have 30, and then 291. I have 35 to 60. I have 40, and then 231, and then I have 45 and 204. So you notice that if I want to approximate y, then I can use Newton's formula depending on the value I want to use. If the value is close to the front, then I can use forward formula. If I'm approximately close to the back, then I can use the backward formula. Otherwise, if I'm approximately close to the middle, then I need to use the central difference formula, which you can find if you go and find the central difference formula. However, assuming I'm given a value of y and I need a value of x, it means I'm finding the y inverse. So find, let me maybe just y inverse of what? Of just which value can we pick? Even 260, 231, even just let me say 250, right? Or in short, what am I saying? This is equivalent to what? Saying find x when y is 250. So you are now reversing the point. You want to find the data point corresponding to a certain measurement that you made in the field. And so I say, since already, what's happening? When you do this, we are just kind of reversing. You are now taking your y as the data point and x as the output. And so we write here the Lagrange. Can somebody, what will be the polynomial here? So I can say that now x, let me just say h of x, which is just a polynomial upon the value of x, is given by what? Is the summation I is equal to 0 up to how many? 0, 1, 2, 3, 4, 5, up to 5. Then we have Li of x multiplied by yi. So this is not y Li, is Li of y, then multiplied by xi. Why am I saying xi? Because I have reversed the process. So it is xi. So x just takes the role of f, and then y takes the role of what? X, just reversing these processes. And this gives you the inverse. You can now find the data points. So for this function, for example, now I want somebody to give me L note, at least we have. Can somebody give me L3 of y? What is L3 of y? The formula.
y minus y naught
y minus y naught
into y minus y1,
minus y1,
y minus y2,
y minus y2,
y minus y3, y minus y4.
hapo nimesimama tena kwanza. Ukisikia nimesimama ujue kwamba kuna shida, kuna kashida.
Oh
There's
yes.
no y
It's a-
minus
there's no
y3.
no
Is
the third y minus. It's done.
is done. Hatujamaliza bwana. First of all, so this is
Y minus y4, y minus y5.
y1, y2, y3, y4, y5. So I'm only skipping these three, right? Yeah, so somebody says here, so y minus y4, and then into y minus y5. You only skip this, the value corresponding to this point. And then divided by, what is the denominator? Somebody else?
y3 minus y naught.
y3 minus y naught.
y3 minus y1.
Mm-hmm.
y3 minus y2.
Mm-hmm.
y3 minus y4. y3 minus y5.
Yeah. So once you know this formula, then it means you can compute all the others. You can evaluate them, and then you evaluate them out. So your y is, look at that. Your y is 250. So you put here, you compute all the LIs. There will be 5 of them. I think there will be 6. And once you compute all XIs, LIs, and then you multiply by the corresponding XI, and then it will give you now the value of X corresponding to Y is 250. So until this point, is there anybody with a question? So silence means everything is okay, right? So we want to move to something else which just borrows directly from what we have done, numerical differentiation and integration. Let me just split them. Let me just deal with one by one. So we want to deal with numerical integration. So we have seen that if we have a function which is so complicated to evaluate, we can approximate that function by an n degree polynomial, depending on the points we have. And so if the points are equidistant, we can use formulas based on the Newton forward, Newton backward, Newton central difference formula. That uses central differences. That's the central difference formula. Otherwise, if the points are not equidistant, we can approximate the function by Lagrangian polynomial, just a polynomial based on the Lagrange. And this happens when the function is either too complex to evaluate, or if we don't know the explicit value of the function, but we know the function has some data points. So in the same way, we may want to find the derivative of the function at some points, or derivative of the function which is complex to evaluate, or function which is only known at given data points. So in that case, what we do is we first start by writing and interpolating a polynomial of that data point, meaning you find a polynomial of the data point. And once we have that polynomial, we can now differentiate it. I told you that these polynomial things, they are nice to work with, very easy to integrate, very easy to differentiate. Just multiply by the power divided by the new power if you want to integrate. No, add 1 to the power divided by the new power, or multiply by the power or the exponent. So being nice tools, that's why we try to express most of the things by polynomials. And so even when you want to differentiate, just use an interpolating polynomial, might be Newton forward, Newton backward, Newton central, Newton or Stirling formula, might be Lagrange. And once you get that polynomial, you now differentiate that polynomial slowly, right? And that's now what we do at the at what? So that's what we do by differentiating. And so we can write a few things, and then we now move to steps. So to differentiate a function numerically, we first write an interpolating polynomial. Polynomial in the interval. In that interval, in the interval given, that is of whatever xn, and then differentiate it. It term by term. To get the approximate derivative. But I've seen that most people do not come to class. Now you are 44. What is your class size?
Around 80.
Around 80, and now I can see only 44. Where are the others? Class rep wengine wameenda wapi?
I'm not sure.
Now I need to capture your names. So we are 45, it means minus my 3, you are supposed to be 42. Can you, each one should write the name in the chat. Write your names in the chat, and then don't write the name of anybody, because I'll cross check. Just each one of you write the name in the chat. And also, I think there was a way of recording the attendance using this thing. It will not happen. But I will take, so they should be 42 names, not more than 42. And then I will take a screenshot of this. If you finish, let me know. Ukiandikia mtu shauri yako. Because I'm actually taking the picture of everybody here, and then I also record whoever was present, and I'm going to check your class list. So nimeachia kwa Samuel Oduor. Yeah, it's good that somebody, whoever types, it comes with the name of somebody. So if you typed a name which is different from the name shown in the meeting, then you are in trouble. So the last name is Masin Zilani Maingi. That's the last name. How? So we proceed. So we have said, so to get this, we get an interpolating polynomial. And so remember what we said, right? That f of x, which is the same as equivalent to f of u. Just recall, I'm just writing the interpolating polynomial, just the four difference interpolating polynomial. And so we can say this is what? F of x not plus u, is it u h or what? Yeah. So this is a substitution we made, but we can write any. So this is the most important one that you can pick here. I'm just basically writing the formula that we did for the four difference. So that is y naught plus u, that's the four difference of y naught, plus u into u minus 1, that is the second difference of y naught over factorial. No, Marigo amekuwa wapi? Huyo Marigo mwenye ameandika. No, when you write, you don't write the number, you write the name and the number.
Nimekuwa
You write your name. I don't want
network
to see
yangu
only
ilikuwa
the
na
number.
break kidogo.
Yeah, write your name and the number, not only the number. Yeah.
So much.
So anybody who comes up to that one, I suspect that they were not finished, so they have been told to. So and then so that's 2 factorial, and then plus, so that is u into u minus 1, u minus 2, and then into y naught over 3 factorial. So you recall this, right? Where x is equal to x naught plus uh, or u is the same as x minus x naught over h, just the same thing we did. And so remember, what do we need? We need to find df dx. So can somebody tell me, how can we find df dx? Remember, we are finding f of u. We want to find f of x, and x is expressed in terms of u, right? So how can we find f of x, where x is expressed as f of u? Do you recall chain rule? Do you know chain rule?
Yes.
Yeah. So I want to find df dx, and x is expressed in terms of u. So it means I have to use chain rule. That means I find df du multiplied by du dx. And so what is du dx from this? What is du dx from here? Ni kama mtasahau kudifferentiate. You have two equations. This is connecting f and u. This is connecting u and x. And so this part will lead you to this, and this will lead you to this. So I'm starting with this because it's just common, it's everywhere, which I'll multiply everything by that one. So what is du dx? Remember, x naught is fixed, h is fixed, so they are constants. The only variables are u and x. So differentiate both sides. That means dx is the same as h du, or du dx is the same as 1 over h. That's what you have at that point. And so having seen this, then it means that df dx is the same as what? 1 over h into, here you can now differentiate term by term. You differentiate term by term, meaning there are different sums. So you differentiate each of these terms with respect to u. Y naught is a constant. If you differentiate, you get 0. Here I have u delta naught. All these differences are constants. So you just only differentiate the variable which is only u. So if you differentiate this part, you get 1. So the first term will be delta y naught, right? And then plus the second term, let me start with this constant. The constant will be delta squared y naught over 2 factorial. And then multiply by, if I differentiate this with respect to u, what do I get? You can use product rule, or if you want, you can expand and then differentiate, right? So if you expand, this is u squared minus u. If you differentiate, you get what? 2u minus 1. So if you have questions, please ask. I'm going slowly so that you can comprehend, because what we need is, because so the only thing you need here is to evaluate the derivative is just to differentiate the polynomial. And so you don't even have to, maybe let me say, cram what the formulas. If you want the first derivative, you differentiate once. If you want the second derivative, you differentiate twice. And then so by differentiating twice again, you don't forget the chain rule still, right? So until this point, are we okay? So the third one is x cubed y naught over 3 factorial. I'm just first overwriting the function, not the constant. If you want to differentiate this also, you can expand it and then differentiate term by term. Or if you want, you can use product rule. By product rule, by knowing that this first term, the derivative, is here already. You did it in the first step, so you can use this product of this. Otherwise, the easiest way to differentiate this is by expanding. I have this is u cubed. Can somebody? So I take use, and then so this by this. So here I have minus 2u minus u, that's minus 3u, times this minus 3u squared. And then by constants, I have That's my plus 2. So that is plus 2u. Now differentiate this. So just confirm that this gives you the same part as this. So if you differentiate it, what do you get? You have 3u squared minus 6u plus 2. And then you can do the same going forward, right? So the thing I want us to find out, remember that here, what happens, assuming we want to find second derivative. So second derivative, that means I want to find df squared over x squared. That's the second derivative. And this can be written as d dx of df dx, right? And remember, this is a function of u. So you need to find this as a function of u. So this can be written as what? As d du multiplied by df du, then multiply by du dx. So basically, these two, let me maybe cycle them. This and this, they are coming from this part. So when you want to find the chain rule, if you want to know that your chain rule is working, you try to imagine that you are canceling out. If you cancel out, then you are going back to the same thing. So assuming assume that I cancel this u and this u, I go back to d dx. That tells you that this is working. And I'm going back to u's because my first derivative here is expressed as a function of u. Where still keep in mind that u is the same as x minus x naught over h. So keep in mind, I'm writing this in several ways. So it's the same thing, just writing it in multiple ways. And so we need, first of all, du dx is h. We know it. So d squared f over dx squared will be the same as what? D du of this. So differentiate this with respect to u. But multiply by h, and h, you will have here 1 over h squared. And then we differentiate now this term by term. Also, this term will go. Differentiate this with respect to u. What do you get? We get 2, right? 2 and 2 cancels out. You get second order derivative of y naught. And then differentiate this with respect to u. Then you get y naught over 3 factorial. Multiply by this is 6u minus 6, right? Let me just write, and then plus these values. Or I can write this as what? 1 over h squared into y naught, and then plus y cubed, so y naught into u minus 1. If I do that, is that okay? Is something happening in your head?
Yes, that's okay.
Okay. So the point is, if you forgot how to differentiate, you can just go and recall what happens. But so the point is, to find an interpolating polynomial, not to differentiate, you first of all get the polynomial. And after you get the polynomial, you now have to start differentiating that polynomial. Even if they want the cubic now, the third derivative, you differentiate this again 3 times. And this same process will happen with the backward differences. So you can repeat this, you can get these derivatives with backward differences, such that if you want to approximate the derivative in front of the or at the initial point, you use forward. If you want to approximate the derivative at the end or the rear end, you use backward formula. So it's just writing down the formula and then you integrate this formula. So one thing I want us to note, what happens if we want your x is equal to x naught? So the question is, what happens if you want to evaluate the derivative at the quadrature, not the quadrature, at the nodal point? So we want to find the f dx where x is equal to x naught. So if x is equal to x naught, what is u? If x is equal to x naught, what is your u?
C1 of h. Or
Can you go back to the formula now, connecting u and h? If x is equal to x naught, what is u?
zero.
So if x is equal to x naught, u is 0. And then we can now evaluate the quadrature point. No, why am I referring to the quadrature? Because I'm thinking of integration. So we can now evaluate the derivative at the nodal point, or at those nodal points. And so you just plug in here, u is equal to 0. That means df dx at x is equal to x naught gives us what? Is given by 1 over h. And then you just start plugging in 0 u. So I'll have y naught over 2, and then plus, that is y naught over 3. If I put this over 3, is it okay? Because 3 factorial is equal to 6. This is 0, this is 0, so you get 2 over 6, which is 3, right? And if you do this, then this will give us what? This will give us 4 y naught over 4. So you can see the pattern. So it's just an alternating. And it's something of this, which function behaves as this, almost like this. It relates to 1 over, it relates to what? 1 over 1 minus x, something like that one. No, 1 over 1 plus x. That's what it relates with, but you have a fraction at the bottom, which you can absorb. But so you see now, this is the derivative. And you can still also find the second derivative at these points. You get this is delta squared y naught minus delta cubed y naught, and you can get those points as you go on. And so basically what I have done with forward difference can be done with backward difference formula, right? And so it's just the same way you can differentiate, you can do this, you can evaluate it. And do we need to do an example? Basically, we don't need, right? Because if you are dealing with points which are equidistant, then you are using Newton's formula to get the derivatives. So you do the same thing. You start by constructing a difference table, and then after getting the difference table, you get it, you write down the formula. If you want to find the value at the back, you use the backward difference formula. If you want to use value at the front end of the table, then use the forward formula, and then you evaluate this. So they're basically the same steps, and everything just narrows down to finding those interpolating polynomials, finding the finite differences, the forward, the backward, and everything. Basically interpreting that table, that's where everything, that's now where you have the foundation. Otherwise, all these other things, you don't even have to cram this formula. You don't have to cram the formula for the second order differences. You don't have to. Why? Because this formula, the only key step you need to know is just this interpreting polynomial. And then just take your time. You can expand it. If you know how to use product rule quickly, you can differentiate quickly. Then this function. And then you have seen that because of this du dx, you are just taking out 1 over h. That's the step size. So this is a formula you can easily get. You don't have to memorize. I will see if we are allowed to write for you the formulas, because some of these things you don't need to basically cram the formulas. You need to know how to use them. So I will check if we are allowed. I will put these formulas at the back. But maybe I don't write which one is which, and I may not use the same variables as what I used. I just write down these formulas randomly and with different parameters. So it's you to find out which means which and which parameter means whatever, and then you put it. But that is if we are allowed to do so. If not, then you have to tell your head to remember it. But what I'm just saying, even if you want to remember, don't struggle to memorize the derivatives. Even the reason I'm not doing Lagrange. Don't struggle to memorize even that when you have Lagrange, if you differentiate, what you get. Don't memorize that one, because it's something you have a polynomial, and differentiating polynomials is something which is quicker to differentiate polynomials. Does that make sense?
Yes, it does.
Yeah. But now I'm kind of tired.
You've had a long day.
Huh?
It's okay. Can't rest.
I had a long day. I've arrived in the house at 9 p.m. and then I start your class. Not even, I think I arrived in the house at 9:30 p.m. That's why I had to start your class 15 minutes late, so that at least I try to make my stomach happy. But so, do you have another class after this?
Yes, we have a class at 10.
So maybe I can 20 minutes is enough to. So numerical differentiation is done. I told you that the same thing we have done can just be done with backward differences. You are just basically having here, you are just only changing these terms, because backward difference is what? U plus 1, U plus 1 plus 2, right? And then you are just differentiating this. So what you will have here, in fact, you will have this backward difference. You will have 2U plus 1, 3U squared plus 6U plus, I think this is minus 2 plus 2 or plus U, whichever, I don't know. And then you evaluate them, then you have backward differences. That's why I'm not going to those aspects. And then you can find this in the books you have and other materials. I can now look at maybe numerical integration. And then, so since there might not be no time for another presentation, I need to add you some assignments. So one, write down the least squares. Formula. So I think this is linear least squares formula, and apply it to an example of your choice. If you want, you can drive the formula. If you want, just read the least squares method and then understand it and then apply to an example. So this is now, you can discuss with your group members, but each person writes their own thing with their own example. If you want to discuss as a group, the 4 examples among you, I think 3 examples, and then each one writes one, I don't mind. But so is an individual, so it means you need to have a different example. And so just when least squares is just part of this, what we are doing here, and what happens with the least squares, like the formula is, you are having, for example, the data points, right? So if you have a linear, then it means you suspect that your data points can be expressed by a linear function. So the least squares method wants to find a line, if it's a linear, that can minimize the distance between the line and the point as much as possible, right? So the points can be given, you have the line, maybe this line can be written as what? X. How do you write the equation of a straight line?
mx plus c.
A plus b. Let me just, yeah, it's the same as, let me just use this, right? I and then I, right? So I'm using hat for the approximate, and then you have what? Yi. So you want to find these values, or A and B. So that's the least squares. Find A and B such that the distance between yi and yi is minimum. That's the least squares algorithm. And so what the distance between yi and, so the distance between yi and yi hat, right? The same as what? The square root between yi's and what? So basically, you are just finding the distance between the points. So we want to find the distance between these 2 points. So it will be xi minus, let me just say this, maybe squared, plus yi minus yj. And then this is squared. So these 2 squared. I'm just first, this is just, I think, the distance between 2 general points. So, but if this has a minimum, the square of this will also have a minimum. And so what we minimize is, we minimize the square of the distances. That's what we minimize. And so we are basically minimizing this distance, yi, and then minus yi hat. That's what we are minimizing. And then we minimize the square, right? And it's the sum of all these distances, the x distances or the y distances, the vertical lines. So so I'm telling you that we are minimizing the vertical lines because the minimum of a square root is the same as the minimum of a square. If you square, you get the same minimum. And remember, what is the approximate value? We said, so this will be the summation of yi and then minus, the approximate value is what? Is the same as a plus b xi. So this is a and then minus b xi squared, because so it is a minus yi, so it's by minus. And so this, we call this the distance a and b. S, y is a function, is the distance, but depending on a and b. And so at minimum, in fact, I'm giving what we are supposed to do. At minimum, the partial derivatives should be equal to 0. So you need partial s, partial A must be equal to 0, and then partial S, partial B must be equal to 0. And so that's what you do basically. Just differentiate this. Let me just differentiate this first with respect to x. So this will be the same as the summation 2 with respect to A, right? So with respect to A, that is 2 comes out, negative comes out. So that's negative. And then you keep this other one minus A minus BXI. That's the derivative of that one. You can check. Just also, I'm also using the chain rule. And then the derivative with respect to B is the same as the summation negative 2 xi into yi minus A minus bxi. So if you simplify this and you put the summations, these ones, they give you what we call the normal equations. So these two are the normal equations. And so these normal equations are the ones which will help you to evaluate. You find A and B, and then you cannot find the approximate values. So you can solve for these equations A and B. So that's the assignment you are supposed to go and finish. But in fact, I've given you everything you need in that assignment. And then to repeat the above for a function of 2 variables. Basically, you are trying to approximate the function which depends on more than 2 variables, right? So you have something like, for example, your yi can be approximated by what? A constant plus bxi plus c, for example, ti. So it depends on x and this. And this, once you know one of them, then you should know everything. Why? Because so the only thing you are doing, you are just replacing this function here. And so here, your s of A, B, C, now there will be 3. Will be the same as what? Will be the same as the summation of yi minus A minus bxi minus cti, and then squared. Because this is the approximate y, and then this is the yi is the data. And this is the approximate value of yi. And so you also differentiate these 3 times. You find partial s, partial A, and then you find partial S, partial B, and then partial S, partial D, no, partial C. So differentiate each of them, you get the normal equations. So I just want you to know how these normal equations look like, so that in the exam you will remember. So in short, this assignment, I'm just sending you to go and read this, but I've given you all the hints you need. And then, so that's 2. So these 2 will be, yeah, I think these 2. Do you need the third one, or you need only these 2? Tell me.
The 2 are enough.
Now the third one is just for your reading now, right? The 2 will be submitted. The third one is just your reading. Polynomial interpolation. Basically replacing the above a function by a polynomial, right? And so you just have also the same way. Yi approximate, you assume is the same as A plus bx plus c x squared plus d x cubed, until so on. And so how this is treated is just treated in the same way as this, where xi is x, ti is the t squared. So you just plug in this, and then you can get normal equations. So here s of A, B, C, D is the same as what? The summation of yi minus A minus bx minus cx squared minus dx cubed, and then squared. And then you can get normal equations. So mostly in the exam, I cannot give you an n degree polynomial because what we just need you to know is, do you know the formula? I can at most give you the 2 points, which is just similar to this. You're just replacing xi by x and ti by x squared, and then you can differentiate this. And where this start from, what I expect to see in your assignment when you explain this, because I give marks for sensible explanation, is that for you to start least squares method, you start by doing what we call the scatter plot. Scatter plot is just what? You will plot the data against this so that you see how your data behaves. And then you find out, can this data be expressed as a linear function? If yes, then you do linear interpolation. If no, you look for the function. That means there are some functions which you can, let me just put this, decompose into linear. For example, if your data follows this law, right? P to power Q or P to power A, something like this. You say that you have been given, no, let me just put this X. You have been given X and Y such that they follow a particular law, because now you are doing engineering and you have so many laws that can describe several things, and not all of them are linear. So you do an experiment, and then you know that this experiment follows this certain law. And so you now want to fit the data to a function that follows that particular law. So like in this case, you want to approximate A and B such that you are having this good fit for your data points. So what do? What happens here is you find out, how can I make this linear? Basically, you transform your nonlinear function into the linear function, right? So by transforming, you find out, assuming this, how can I make this look like a linear function? Basically, you are trying to find this b in the form of y is equal to a plus bx. What can I do?
To use a logarithm.
Logarithm.
Yes, right. So you have ln of y is the same as ln of b plus a ln of x, right? Are we okay if I write that way?
Yes.
Yeah, so it means now you have your new data. I can call this y, I can call this x. So you get your new data x and capital Y, such that now these are the linear logarithm of these values. And you now apply your least squares algorithm, b plus a x. And so once you get capital B, you know that b is the same as exponential of, this is ln of b. So this is expressed in terms of what? In terms of the b. And so you know that b is the same as, what you get is the ln of b. So you can get b by finding the exponential. And so that is what you do. So basically, when you get these laws, you find out how can you transform this into linear. If I give you, for example, y is equal to 1 over x minus b, even a, right? What can you do to convert this into linear? What can you do? Anybody who knows? Mhm. What happens if you find the reciprocal? Then find this, you get that 1 over y is the same as what? Ax minus b, right? Which I can write was what? As b plus ax, where b is equal to negative b. And so you now have your new data set. Y is the same as b plus ax. So you now have your new table. X remains as x, and then you have here 1 over y, which is capital Y. And so you can transform that way. So so basically what is happening here is, once you understand the linear, then you can transform the nonlinear into linear, depending on what you are given. And so you just need to go and practice how do you transform this. So these others, you just need to read on your own, but the ones to be submitted are these two, alongside the others I gave you. And if you have questions in this, even if these submitted assignments, we are not doing this to punish you. We want you to learn. So even if you have questions on the assignment, you are not sure, I'm still happy to clarify. I will not do for you what you have, because you have your own example, but I'll try to explain to you alongside the steps you have. So if you are stuck, feel free to ask your friends, or you can ask me. Even in this, if you get examples this way you are stuck, feel free to ask me. So next week, I will do two things. I will finish up numerical integration in the first 1 hour on Tuesday. The second hour, I will start on differentiation of ODEs. And then I can just only touch on two methods. One is the common one, which is the Euler method, which is introduced to everything. And then I can look at which is the common one used is the Runge-Kutta methods. And if time allows, I do multi-step methods, at least one of them, just examples, so that you get a flavor of what you need. Aha. Sasa yangu imeisha. Mwenye akona yake anaweza sema.
Yes, I have a question. Yeah, the least squares, the numerical differentiation, and basically everything we've been looking at, are they the techniques that are used in neural networks backpropagation?
All these techniques are used, is that some of them which are used are more advanced than this. But these are the foundations, right? So once you learn this, then you can move on into some of more complicated functions that can do multiple things, so that when you have complicated scenarios. So everything starts from this. This is the foundation. So in class, we cover the foundation. That okay?
Yes, and what's the best way of attacking this AI thing? Do you start by understanding of course, the math is the foundation, or do you just be one of those people who just you take, let's say, the blocks that people have built, and now you use them, for example, the GPT and all these other algorithms? What's the best way for, let's say, us
Now,
do you start with the
even in the programming, this AI is na msipochunga itaenda kutoa watu kwa kazi. But what I recommend is, even if you go to ask the AI, the chat GPT, to give you the code or to give you something, start by understanding the basics. So if you understand the basics, then even if you go somewhere, because you find nowadays there are so many people who have constructed the codes that can do multiple things. But if you don't have the basics, then you cannot even read their code and understand. Or if there's something which is not working in their code, then you are not able to trace and get help. So even if you are using AI to supplement what you do, or to get some of the key parts you are lost in, start by getting the general layout of what you need, or understanding that I want my program to do this. And maybe first part, I need to do Gaussian elimination. Second part, I want to do backward substitution. Third part, I want to do this. So that becomes the code, the basic. Then the second part, now, I want my code to do pivoting. What do I do? So if you know those basics, and even if you go somewhere and get a code that does the same thing, you'll be able to follow that code and be able to understand each of these parts. So just start by understanding the basics, then the rest can be sorted out.
Thank you.
Any other question? Kama hakuna, now you are free to leave.